Welcome everyone to our presentation. Before we begin, let me introduce our team briefly. My name is Phạm Văn Tiến. Currently, I am a software engineer at Viettel High Technology Industry Corporation. The co-author are Professor Trần Thanh Hải and Professor Vũ Hải. Both are lecturers at School of Electronics and Telecommunication from Hanoi University of Science and Technology, and also researchers at International Research Institute (MICA). Today, I am going to be talking about our paper, Detection and Tracking Hand from First-Person View, Benchmark and Challenge on Rehabilitation Exercise Dataset. Our presentation consists of 4 parts. Firstly, I will introduce the context and motivation of our research, challenge, and related work are also reviewed. In the second part, proposed framework are described. Next, we're going to give detail of the dataset. In section 4, we analyze experimental results. And finally, I will make some live demos. Okay, let's get started. Egocentric vision is an emerging field of computer vision characterized by the acquisition of video from the first-person perspective, particularly for evaluating upper extreme rehabilitation. Egocentric vision offers the ability to quantitatively measure the function of hands used in physical and base exercise. The context of this research is the project's understanding human daily life activity from egocentric vision using advanced technology of deep learning sponsored by NAFOST, which is conducted at the Rehabilitation Department of Hanoi Medical University Hospital and MICA Institute. As you know, first-person view requires the analysis of video captured by camera on the head or chest that imitates vision of the user. The visual data are mostly focused on the performing tasks of the user, and therefore it provides a valuable perspective to understand the user's activity and also the relevant context. This study emphasized on an important component in the egocentric vision, hand, which is omnipresent and of primary importance for human beings. Their position, pose, configuration, and trajectory intuitively tell what the wearer aims to do or what he or she pays attention to. Further, the output can be then inferred in higher level to obtain certain objectives. Therefore, hand localization and tracking are principal issues in first-person view with a heap of use. Results of relevant works have to deploy first-person view-based systems like human-machine interface, augmented reality, virtual reality system, learning control in robotics and healthcare systems. In this paper, we report the critical task of the hand from first-person view using the state-of-the-art deep neural networks. The problem we will do is the first detection, the bounding box of the hand, and we will also have to track the identity of each hand from the surveillance video to get the hand's location, identity, and trajectory. Like in this video, as you can see, we have two hands. The hand from first-person view presents typical advantages and drawbacks when compared to third-person vision, when sensors are generally steady and disconnected with user. The main superiority of first-person view is that the hands and operated items are more likely to occur in the image center, as well as hand occlusion are minimized, which interpreting hands motion appears to be a basic human skill. Machines face a significant hurdle because of hand gesture is complex, as well as variation in illumination and orientation. Researchers must also encounter distinctive issues when working in first-person view, such as the camera's dynamic and unexpected shifting, strong ego motion, considerable blur and sophisticated hand-object manipulation. The sensor is steady because it moves in sync with the wearer. It occasionally produces quick movement and abrupt lighting changes, making it harder to isolate the hand and item focus from the backdrop. Many works approach hand detection by using reason-based DNA. We have a probabilistic method for reason proposal initiation, which is successful by combining spatial bias in a prior model and then classifying the reason using cabinet. Other authors suggest some two-stage model in which hand reason proposed at first using probability map or skin color or deformable path model, and then the proposal will be processed by a pre-trained CNN to determine bounding box. The probabilistic model are not zero since its accuracy strongly depends on the hand's position and skin color in the training phase. Faster CNN are employed for recording hand movement of people with spinal cord injury at home. In some research, and also kernelized correlation filter is used, and motivated by real-time application requirement. Some works attempt to predict the future hand's position by using temporal model mixed with detection results. Also, the detection-free strategy is great computational cost by not running the hand's detection every single frame. This method isn't comparable with the checking by detection approach in precision. It is remarkable that all of the aforementioned works tackle this problem within a specific object detection or checking algorithm, only while the framework presented in our paper is an open tracking by detection pipeline, allowing to integrate any other algorithm. Our proposed framework consists of two main phases. The first one is the detection or segmentation phase, and the second one is the checking phase. From the input video sequence, we will detect the bounding box and the class along with a confidence score of all the hand in the frame, and then all the proposed bounding box will be matching by applying the checking algorithm like sort or deep sort. After applying the algorithm, the hand's trajectory is presented. This picture presents the RCN model family, which is the main algorithm in the detection phase. The next one is the YOLO model family. We used in this paper we adopt YOLO version 4, the latest version from the YOLO model family. It improved on version 3 with several bugs of feature and models such as weighted retinal connection to achieve robustness along with an impressive accuracy. Next is the sort and the deep sort algorithm. For each coming frame, sort propagates objects that are already checked in the current frame. The new position of the already checked objects are predicted using a Kalman filter with a linear constant velocity model. Next, a detector detects objects present in the current image. The detected objects are then compared to previously checked items, and a ghost metric is calculated as the value of detection, and each of the formerly checked object detections are then assigned to already checked object using the Hungarian method. When an object is detected in 3 consecutive frames and does not overlap any other checked object, a new trajectory is created. This shot is built to reduce the number of identity squares and integrate appearance information into the tracking process proposed in the shot. The first improvement of this shot is the deep appearance descriptor used to extract features present from previous frames. It is actually a convolutional neural network trained on a person re-identification dataset. To adapt this to an egocentric hand tracking problem, it is first require an egocentric hand re-identification dataset to train the appropriate appearance descriptor. According to recent review, there are just a handful publicly available egocentric hand re-identification datasets. So from the analysis of 3 datasets, we build a new egocentric hand tracking dataset. This dataset will be described in the next part. And after obtaining the egocentric hand tracking dataset, we change the appearance descriptor. Descriptor of incoming detection is then compared to the descriptor of tracked object by calculating the cosine distance between them. Tracked object and their appearance descriptor are also saved for 30 frames after they lost, so that this shot has the ability to resume tracking identities that have been lost for a number of frames. And also we need to pay attention to the Mahalanobis distance, which is the smallest cosine distance in the appearance space. This slide shows the egocentric vision datasets. Our data collection consists of 3 datasets: the EGT gaze dataset, the ego hand dataset, and our new dataset, MyK Rehab. Okay, the EGT gaze is a large and comprehensive dataset for first-person view action and gaze. It assumes GT gaze and comes with high-definition video, audio, gaze tracking data, frame-level action annotation, and pixel-level hand mask as sample frame. The datasets can be found in this link. Next, the ego hand dataset contains a 48 Google Glass video of complex first-person interaction between 2 people. The main intention of this dataset is to enable better data-driven approach to understanding hands in first-person computer vision. More detailed info about the structure of that dataset can be found in this link. Okay, this is our new dataset, the MyK Rehab dataset. The evaluation utilizes an egocentric hands detection and tracking dataset named MyK Rehab. The dataset consists of rehabilitation exercise of patients through interaction of their hands with daily living objects. The dataset is collected at Hanoi Medical University Hospital with 10 persons who wear cameras under the supervision of the doctor and the help of the authors. The patient performed 10 types of actions such as practicing with a bowl, with a bottle, with cup, and playing with toy. And we developed a semi-automatic data annotation tool for labeling the data. The principal idea is to train the model on available datasets at first, and then generating proposed on unlabeled data, and finally adjusting ground truth if necessary. The pipeline allows the annotator to mark both bounding box and trajectory of hands, and also support many models, such as importing data, selecting model, viewing ground truth, debugging, and exporting output to multiple formats. Through this tool, subjectivity of human perception and loss of time are reduced, as well as consistencies and coordination among different individuals' annotations are accomplished. You can find the tool at the link in this presentation. Next, we will describe our evaluation criteria. We have three main criteria. The first is the object detection matrix, and the second is the object tracking matrix, and finally is the performance. And all experiments are conducted on a GPU, on a graphics card GTX. We use the COCO protocol since this is the most popular matrix where average precision and average recall are averaged over multiple intersection over union values, and IP from 0.5 to 0.95 refers the average precision for IOU value ranging from 0.5 to 0.95. You can find the tool for this evaluation matrix at this link. The object tracking matrix is measured according to the MOT 60, where it is the multiple object tracking in the year 2016, where the most important metrics are multiple object tracking accuracy, multiple object tracking precision, IDF1, and identity switch. Here we have the egocentric hand detection and segmentation results. Concerning egocentric hand detection performance, this table shows evidence that two-stage detector represented by the RCN family models generally outperform the one-stage detector, the YOLO model family. For IP, the IP50 obtained by mass RCN and faster RCN are nearly 89% and 87% respectively. This points that mass RCN generate an impressive segmentation result, while the fast RCN additionally present an awesome detection quality, where the average precision is pretty high, 96%. YOLO version 4 gives a remarkable performance with 95 average precision and 72 average precision medium. YOLO version 3 adapts well in predicting large hand. It obtains 54%, but it is still worse than the mass RCN, which acquires 92%. In terms of average recall, again, the fast RCN performs the best performance with 97 for both average recall. This means that this model can detect almost large hand in the dataset. And this table measures the machine's memory requirement and the processing rate of object detection phase when inference model. We noticed that one-stage detector represented by YOLO model family completely outperformed two-stage detector. YOLO version 4 performed a real-time speed 25 frames per second on a normal machine, which requires only 2 GB RAM and 2 GB GPU memory at inference stage. Processing rate is slightly reduced in case of YOLO version 3 with 22 frames per second. The mass RCN takes up to 250 milliseconds computing time for each image, and thus the speed is only 5 frames per second, and it is not adaptable for real-time processing application. And also it requires a huge memory. And finally, the fast RCN seems to get balanced trade-off between precision and speed in the remaining case. Okay, different results for combination of tracking and detection algorithm are reported in this table. Further, ground truth detection are also tested with short and deep shot. Their combination of for detection model with two tracking algorithm, short and deep shot, give a total 10 options for the pipeline conventionally and respectively defined, and such as Y3S means YOLO version 3 with short, MDS means mass RCNN with deep shot, GDS means ground truth with deep shot. The overall tracking evaluation on Micaria say that deep shots generate a higher multiple of the tracking accuracy in almost K. As you can see in this graph, it is reasonable to conclude that the better detection model is, the higher tracking quality is. Okay. In the next part, I will analyze some challenging cases that remains in this research when hands are occluded by other obstacles. Tracker lost information about the hands due to the detector naturally cannot find the hand. Like in this, the right hand at frame 200 is at identity 1, but in the frame 259, this hand is occluded by a toy, by a home toy, and then in the 282, the right hand is initialized with a new tracker with identity 7. Next, when the hands move rapidly so that the cameras cannot catch, this makes the motion blur phenomenon occur. As a result, detector fails to predict the existence of the hand. Like in this, a new tracker initialized for this hand because it is blurred in the frame. And when the shape of the hand changes heavily, the deep appearance descriptor doesn't work well. It could not recognize that the different shapes belong to a same ID. Consequently, a new ID is initialized as a new tracker. In this frame, the deep shot works stable on this right hand, but when the two hands are equal motion, the tracker cannot differentiate two hands and it initialize a new ID for the hand. Okay, in the next part I will make some live demo. All of the codes and data in our research are published in this GitHub link. Okay. This is the link with all the instructions to reproduce our result. First, you can refer the installation in this file, and all the models are trained available in the model tool, and the dataset is also description. Let's get started. The dataset rules. You can prepare the data format like this format. And after running the visualization code, it will show the gratitude for the input video and also save the output video like the following. This is the gratitude, and a full 32 original quality gratuitous videos are also uploaded to this YouTube link. Let's this one and more video here in here. Okay, and thank you for your attention.